Hello guys, I'm really thrilled to see you again. Today we will complete the journey on basic integration techniques as we learn integration by parts. Let us consider the integral of x e to the x dx. Now, this is not an integral that was listed from the basic ones, and substitution is not a clear option because we have two possibilities. First of all, is considering u equals e to the x, but its derivative is not part of the integral. And the only remaining option is considering u equals x, and its derivative is part of the integral as dx. But if we do the substitution, we end up having the integral of u times e to the u du, which is basically the first one, but with a different variable. So we need to consider another technique. Now, this is what we're going to do in order to solve this integral. Follow me on this one, okay? We're going to take one of the functions and we're going to name it u, and we're going to differentiate this one. And we're going to take the remaining one and we're going to call it dv, and we're going to do the integral of this. In our particular example, we're going to take x as u, and if we do the derivative of u, we get du equals dx. And if we take dv equals e to the x times dx, and if we do the integral, we get that v is equal to e to the x. Now, integration by part establishes the following. The original integral, the integral of u dv, which is the integral of x e to the x dx, will be equal to u times v minus the integral of v du. Now, the integral of v du, after applying the proper substitution, is the integral of e to the x dx, which is equal to e to the x. So the final result for the original integral will be equal to x times e to the x minus e to the x plus c. Now, the general statement regarding integration by parts is the following. If u equals u of x and v equals v of x are differentiable functions, then the integral of u dv is equal to u times v minus the integral of v du. The general idea for using this technique is to take u as the function that can't be integrated, or at least the function which, after differentiation, it simplifies the original integral. And after this, we can take dv as the remaining function. Let us consider the integral of x squared arctangent of x dx. Notice that the function arctangent of x is a function which we don't know its integral. Thus, we have to take this as our variable u. Thus, if u is equal to arctangent of x, then du is equal to dx over 1 plus x squared. Therefore, we have to take dv as x squared dx. So if we integrate dv, we get v equals x cubed divided by 3. Now, remember that the original integral will be equal to u times v minus the integral of v du. So, if we do the substitution, we get that this integral is equal to x cubed times arctangent of x divided by 3 minus a third of the integral of x cubed dx divided by 1 plus x squared. So, for solving the whole integral, we need to know what a third of the integral of x cubed dx divided by 1 plus x squared is. By applying polynomial division, we get that this integral is equal to a third of the integral of x dx minus a third of the integral of x dx divided by 1 plus x squared, which can be solved by using the substitution technique. Thus, the original integral will be equal to x cubed arctangent of x divided by 3 minus x squared divided by 6 plus the natural logarithm of the absolute value of x squared plus 1 divided by 6 plus c. Now let us consider the integral of x times secant of x times tangent of x dx. Notice that we know the integral of secant of x times tangent of x dx, which is equal to secant of x. So this is a very good candidate for dv. Thus, we can take u equals x for simplifying the original integral. So if we do so, we have that u equals x leads to du equals dx. And if we take dv equals secant of x times tangent of x dx, then v is equal to secant of x. Thus, the original integral will be equal to u times v minus the integral of v du, which is x times secant of x minus the integral of secant of x dx, which is equal to the natural logarithm of secant plus tangent. Thus, the original integral will be equal to x times secant of x minus the natural logarithm of the absolute value of secant of x plus tangent of x plus c. Some of the integrals require a little bit more work. For example, there are some times in which integration by parts has to be used more than only one time. Let us consider the integral of x squared times sine of x dx. And we're going to say that u is equal x squared, so du is now 2x. And dv is equal to sine of x dx, so v is equal to minus cosine of x. So if we apply integration by parts, we know that the original integral will be equal to u times v minus the integral of v du, which is equal to minus x squared cosine of x plus 2 times the integral of x cosine of x dx. And for solving this integral, we're going to use integration by parts again. We're going to say that u is equal to x, so du is equal to dx. And dv is going to be cosine of x dx, so v is equal to sine of x. Thus, the integral of x cosine of x dx will be equal to x times sine of x minus the integral of sine of x dx, which is equal to minus cosine of x. Thus, if we put all the results together, we end up having that the original integral will be equal to minus x squared cosine of x plus 2x sine of x plus 2 cosine of x plus c. The whole world of calculus is divided by a huge amount of parts, which you have been learning so far. I can't wait to see you making more progress. I challenge you to solve the following integrals by using integration by parts. And as always, see you in the next lesson.